Alright guys, so in this video, we're going to cover everything that you need to know for the weak acids and Ka topic for AQA A-Level Chemistry. I'm going to go through this specification for you step by step, making sure I cover everything you need to know for your exams so that you can wrap your head around the methods involved and see exactly what you need to do to get those A's and A stars, alright? So let's get started. First off, let's look at the specification itself and see what do you actually need to know. So the first point here we have is weak acids and weak bases dissociate only slightly in aqueous solution. And I'm going to break down each of these in more detail in the next slides, okay? Next point, Ka is the dissociation constant for a weak acid. And here we have an equation that you need to know, okay? pKa equals minus log to the base 10 Ka. All right, so that's the first 3 points out of the way. Next up, what should you be able to do as a student? You need to be able to construct an expression for Ka. You need to be able to perform calculations relating the pH of a weak acid to the concentration of the acid and the dissociation constant Ka. If you're a bit confused, we'll break it down in a second. And then lastly, you need to be able to convert Ka into pKa and vice versa. This last box that we have here for skill development is normally overlooked in the specification, but it's really important because they actually bring out these within your questions. So first off, carrying out pKa calculations and giving appropriate units. This is standard and it could pop up in any acids and bases exam question. Next up, you need to understand standard form when applied to areas such as, but not limited to, Ka, and you need to be able to calculate Ka of a weak acid by measuring the pH at half neutralization. And we're going to break all of these down in this video. So the first point that we had here, weak acids and weak bases only slightly dissociate in aqueous solution. So we're only going to focus on weak acids in this video, and we're going to ignore weak bases for the time being because that's what this topic is about, weak acids. So what does dissociate mean, okay? Dissociate is just a fancy word for ionize. So it just means to break up a compound into separate ions, one being positively charged and one being negatively charged, okay? So let's look at a typical equation that you would see for the dissociation of a weak acid in solution. So HX, okay? Now this is normally the symbols given to a weak acid, the H being the hydrogen ion or the proton, the X just standing for the remainder of the weak acid. This can be anything. We'll look at an example in a little bit. Sometimes this HX is replaced with an A, so you'll see it as HA. They're interchangeable and AQA can throw either of these at you. It's just an algebraic value to define the weak acid. Next up, H2O. Okay, so solution, there's going to be water present. And you'll notice here, we've got a equilibrium arrow, okay? This is very different to what you would see in a strong acid dissociation, where you would see the arrow going only in one direction, from the reactant side on the left to the products on the right. But this is not the case here. This is an equilibrium reaction. So this forms our hydronium ion, H3O+, and our X minus, our anion here, okay? So the HX, the weak acids, acting as a proton donor, a bronzosylary acid, donating the proton onto the water, H2O, and forming the H3O+, okay? So just to illustrate this then, let's think of a beaker filled with some weak acid. The most typical you'll probably see is ethanoic acid, which you may have used in your class. We're going to be adding that to a conical flask of water, so solution. When you add that weak acid in, that ethanoic acid is going to ionize or dissociate, okay? And that's what's happening here in this equation, right? That's just a quick example for you to visualize it. Now, we will always simplify this. So what will we simplify this equation to? We will just get rid of the water entirely from the equation since it's present on both sides, okay? So you would simply have HX dissociates or ionizes into its separate ions, the H plus ion or a proton, and our X minus, or sometimes, like I mentioned, you may see it as A minus, depending on what question you're looking at. So that's the first point done, okay? Next point on the specification, Ka is the dissociation constant for a weak acid. There's nothing too much you need to understand here. Just remember that if they ask for what is a dissociation constant for a weak acid, you would put Ka, but it will never be this simple. It will normally be some sort of calculation. And as we'll look at in a second, you'll need to write out what the expression is. So this word you'll see come up with slightly dissociate. What does this mean? So if something only slightly or partially dissociates or ionizes, the equilibrium lies to the left. Okay, so the weak acid barely breaks apart into its constituent ions, the ions that make it up. So the way that you can think of it is it sort of holds its form, it holds its bonds together, and it doesn't break up in solution. Okay, so that HX, or going back to our previous example of ethanoic acid, most of the equilibrium is going to lie to the left of the equation, meaning that the ethanoic acid is formed and not really broken down into its ions. Okay. So going on to the skill development portion of the specification, we need to understand standard form when applied to areas such as Ka. Okay, now this will pop up all the time in chemistry. So hopefully you're familiar with standard form. It's a GCSE concept, but let's say we're looking at the Ka of ethanoic acid, right? This is 1.74 times 10 to the minus 5 moles per decimeter cubed. Now this is standard form. And if you want to put it into a normal decimal format, it would be 0.0000, so 4 zeros, 174. Okay, all you do is move the decimal place 5 points to the left, hence the minus 5. Okay, wrap your head around that, practice a few questions, and you should be completely fine. Hopefully, at this point in A level, you should be really comfortable with using standard form, but it's just there in the specification, so make sure you know it. Okay then, next up, you should be able to construct an expression for Ka. Okay, this is really easy. When you get a hang of it, it will make so much sense. So let's say we have our equation that we used previously, our HX dissociating into a H plus and X minus ions. Okay, now a better way to understand this would be to use our ethanoic acid example, just so that you can visualize where the ions are and what's happening. So here, just as HX, we're going to be using our ethanoic acid, CH3COOH. Okay, as you can see here, the X portion is going to be our salt, and then our H portion is our proton. And when that breaks up, we get H plus CH3COO minus, which is called ethanoate ions. Now, just like Kc, if you guys have done Kc before, the Kc expression is always written as concentration of products divided by concentration of reactants. And it's exactly the same thing for Ka, guys. So in this case, you would have Ka equals, what are the products for this? It's going to be our H plus and our X minus, or our H plus and our ethanoate ions. And then under that would be our reactants, our HX, or our weak acid in its compound form, ethanoic acid. Okay, and if you remember it like this, and let's say, for example, in a past paper question or in your exam, it says, please write out the Ka expression for ethanoic acid, propanoic acid, butanoic acid, any of the weak acids, you would literally just do, what are the products? In this case, it would be H plus and the ethanoate ions, square bracket that up to denote concentration, and divide that by the reactants, which is the complete weak acid, the ethanoic acid, which is our reactant. Okay, just wrap your head around this, exactly the same as Kc. So easy, just try and remember that. And after a while of practicing, you'll know it off by heart. Okay, so the next thing you need to be able to do is to perform calculations relating the pH of a weak acid to the concentration of the acid and the dissociation constant Ka. So going back to our really simple ethanoic acid example, I'm going to chuck that equation on the screen again for you. And I'm going to detail some assumptions that we make when it comes onto the dissociation of the ethanoic acid. The first one being that the concentration of H plus at equilibrium, so once the solution has completely reacted and it's reached equilibrium, that is going to be equal to the concentration of the salt or the anion, or X minus, A minus, you may see it in different forms. And that is because they dissociate in a 1-to-1 molar ratio. So if you look at our equation at the top, you can see there's 1 mole of H plus and 1 mole of CH3COO minus. Okay, they dissociate in a 1-to-1 ratio, so we can assume that they're going to be equal. And also, in these instances, remember the equilibrium is always so far to the left. Okay, so it's going to barely dissociate. So the small portion that does dissociate is going to be in a 1-to-1 molar ratio. So they're going to be equal. Okay, that's the first assumption. The second assumption is that the initial concentration of the undissociated acid remains constant. Okay, and that goes directly back to what I just said. The equilibrium lies so far to the left in this case, and the cases of all weak acids, that when you first put the weak acid in that conical flask, like I showed on the first slide, it dissociates so slightly that the initial acid concentration equals the weak acid concentration once it has reached equilibrium. And that's because it barely dissociates. So really try and wrap your head around that. So why do we care about these assumptions? Why do we care at all? Okay, and the reason is you need to be able to use them in calculations. So going back to our Ka expression, okay, Ka equals H plus concentration times X minus concentration over our Hx, okay? We can simplify this to Ka equals H plus squared, all right? And the reason we can do that is because our H plus ion, if you look at our first assumption, our H plus ion equilibrium concentration is equal to our X minus concentration equilibrium. Okay, if they're the same, think of it, let's say the H plus equilibrium is 2 and the X minus equilibrium is 2. 2 times 2 is 2 squared. Same thing, okay? They're identical, so we can just chuck that assumption on the page and just square them up, divided by our Hx, okay? Keeping it exactly the same on the bottom of the fraction, but just making the assumption that we square the top. This is key. This is so key. I really want to drill this into your head because you need to do this in pretty much every single Ka calculation. However, do not make these assumptions if you are asked to write the full Ka expression. For example, the AQA exam question would literally write something along the lines of, write the Ka expression of propanoic acid, okay? You do not want to make these assumptions. You want to write it out in full as it is on the left. Do not square it. Okay, this is really important. They will not give you the marks for that. Second thing you don't want to use it for is buffer calculations. Now, I've made a video on buffer calculations and I will make some more, but just for the time being, please do not use this for buffer calculations as you will get it incorrect. You do not need to know the theory behind this. Just avoid using it for Ka expression questions and doing buffer calculations. But if there are any calculations just around Ka, not buffers, then please use this because you will get the marks, and that is the correct method. So I'm going to go through a Ka calculation question, but just before I do that, I wanted to look at this point because it feeds into our calculation question, and this is some knowledge that you need to be aware of. So the next point in this specification, you should be able to convert Ka into pKa and vice versa. Okay, and these are some equations that you must remember. So think about pH, okay? Just any sort of strong acid or any acid calculation, you're going to be using pH in some way. So do you remember what the pH equation is? So it's pH equals minus log H plus ion concentration. Now you will see it sometimes with base 10, sometimes without base 10. It doesn't really matter. As long as you're pressing the log button on your calculator, you'll be fine. Now, if we want to rearrange this to work out what the H plus ion concentration is and make that the subject, all you have to do is the inverse log function, okay? So if you have a Casio calculator or something like that, you'll normally just have to press shift, log, and that will be 10 to the power of something, okay? And in this case, you will always do 10 to the power of minus pH, okay? And this is just the equation rearranged to make H plus ion concentration the subject. Now, let's look at pKa. What is the equation for this? Now, in the specification, it tells us that pKa equals minus log 10 Ka. Now, does this look familiar to you? To me, it looks exactly the same as the pH expression. However, it's just changed H for Ka, right? So, what I like to teach my students is that think of the lowercase p as a minus log. And if you do this, it's so easy because then you have on the top equation, you have lowercase p, okay, minus log H plus ion concentration. And on the pKa one, the lowercase p, you have minus log and then Ka. Simple as that, okay? And just in the way that we did the inverse log for pH to make the H plus ion concentration the subject, you do exactly the same thing for pKa to make Ka the subject. So it would just become Ka equals 10 to the minus pKa. Okay, so that's that part ticked off the specification. Let's move on. So we've got some skill development here. Okay, calculate the Ka of a weak acid by measuring the pH at half neutralization. So I'm not actually going to break that down in this video. I've already done a very in-depth past paper question on this from the AQA specification, and I'll link that in the description below because it goes into far more detail than I would in this video. So check that out if you're not too sure about calculating Ka at half neutralization, okay? So with that out of the way then, let's move on to our cheeky Ka calculation question. So this is from a past paper and I've reworded it slightly to avoid copyright, good old AQA, but the acid dissociation constant Ka for ethanoic acid is given by this expression. You're probably sick to death of ethanoic acid by now, but it's the most common one you're going to see, okay? So the Ka of ethanoic acid is 1.74 times 10 to the minus 5 moles per decimeter cubed, and it tells us that a buffer solution was made using ethanoic acid and sodium ethanoate, and it has a pH of 3.87. They also tell us that the concentration of ethanoate ions, so our X minus or A minus, also referred to as our salt, in the buffer is 0.136 moles per decimeter cubed. And we need to calculate the ethanoic acid concentration in this buffer, and we need to give our answer to 3 significant figures. Standard stuff here, guys. So, hopefully you realize something. It mentions that it's a buffer solution, so we cannot make that assumption where we just replace the Ka expression at the top here to be H plus squared. We cannot do that because it's a buffer, so just keep that in mind. So the way I would solve this is just look at my Ka expression, okay? They've given it to us for a reason. They just haven't chucked it on the page for no reason. They've given it to us because we're going to have to use it. So let's tick off what variables we have one by one. So Ka, first off, we have that as 1.74 times 10 to the minus 5. Tick that off. We also have the ethanoate ions, 0.136 moles per decimeter cubed. Tick that off. And they want us to calculate the ethanoic acid concentration. So that's the bottom of the fraction. So that's what we need to make the subject. So what's missing then? Our H plus ion concentration. So we need to work out our H plus, but what else do we have? We have our pH. And just in the previous slide, I showed you that you can do the inverse log to calculate the H plus ion concentration. So let's do that right now. So H plus ion concentration equals 10 to the power of minus, what is our pH? 3.87. Okay, so chuck that in your calculator and you're going to get an answer of 1.349 times 10 to the minus 4 moles per decimeter cubed. Okay, so that's our H plus. Now we have that variable as well. All we have to do is rearrange the expression to make the ethanoic acid the subject. Okay, hopefully you guys are okay with rearranging. So if you do that, then we're going to have our ethanoate ion concentration on the top as 0.136, bracket that up, multiplied by our H plus ion concentration that we just calculated, 1.349 times 10 to the minus 4, divided by our Ka, which is given in the question as well, 1.74 times 10 to the minus 5. Okay? Put all those juicy numbers in your calculator, and you're going to get an answer of 1.05, and that is to 3 significant figures as it specifies in the question. Okay, now it's very similar to other amount of substance questions. You got to think to yourself, what have they given to me in the question, and how can I use this to my advantage? What variables do we have? What do I need to rearrange to make the subject? Okay, that's what your brain should be thinking when you're going through these questions. Right, guys, that's it. That's the end of the video. But first off, let's go for a spec check, ensuring that you've covered everything you need to know. That's how you want to get your A's, A stars, guys. Learn what you need to know, practice the questions. Okay, first off, weak acids and weak bases dissociate only slightly in aqueous solution. Bang, we did that. Ka is the dissociation constant for a weak acid. We looked at that as well. Very simple stuff. pKa equals minus log base 10 Ka. Okay, we looked at this equation in detail and we broke it down. Next up, what should you be able to do in preparation for your exams? You need to be able to construct an expression for Ka. We checked that out. You need to be able to perform calculations relating the pH of a weak acid to the concentration of the acid and the dissociation constant Ka. We did a calculation for that just now, rearranging them all using each of the variables. You also need to be able to convert Ka into pKa and vice versa. We looked at that with the inverse log. Okay, skill development. What is this section? We need to carry out pKa calculations and give appropriate units. You want to carry out the same methodology, thinking, what equations do I know from the specification? How can I rearrange these and what variables has AQA given me? Simple as that. Next up, understand standard form. Hopefully this is second nature by now. You should be comfortable with moving the decimal places to the left or the right, depending on whether it's a positive power or negative. Lastly, then we have calculate Ka of a weak acid by measuring the pH at half neutralization. And as I mentioned, guys, I've got a very detailed past paper question breakdown that involves exactly this. It has the graph, it has the theory behind it, and the methods that I would follow. So please check that out if you're not too sure how to do this. I hope you learned something from this video. I hope it was helpful. I put a lot of time into it. Like the video if you did. Subscribe for future science and maths content. All the best in your revision and upcoming exams, guys. Just try your best. Don't stress too much and you'll be fine. Peace.